Good evening, guys. How are you? I hope you're doing well. This is going to be lecture 7. We're going to be talking about voltaic cells today. This builds on what we did last time, talking about redox reactions. We're going to learn how they can be practically used, one of the practical applications of redox reactions today. I'm going to go ahead and start sharing my screen so that you guys can follow along with what I'm doing. And I will do the same thing that I did last time and post my handwritten notes along with this so that you can see some of the drawings and stuff, because I'm finding it very difficult to do it in this particular fashion. So I hope that's okay with you guys. Let's go ahead and get started on our material. Let's see what we're going to talk about today. So this is all from section 2 in chapter 18. We're going to be talking about something called voltaic cells. We'll define that in a few minutes. And then we'll be talking about the cell notation that's used for voltaic cells. These are questions that are going to go along with your laboratory. Please understand that the diagrams that I'm going to show you today are a little different than what happens in the lab. Make sure that you read the lab manual about what happens in the lab, since you're not physically going into the lab, because there is a difference between what I'm going to show you today and what's done there. I'll talk a little bit about it, but I'm not going to talk a lot about it because those are your lab points, so that's not my place to give you. All right, so questions, comments, problems. Hopefully there's nothing, but if there is anything, please, I hope you know by now, reach out. Send me an email, give me a call, come to my office. We'll set up a WebEx, whatever it is you need. We'll figure it out. Okay? Thanks, guys. I appreciate it. So voltaic cells. Now this is a general diagram for a voltaic cell. I'm going to talk about them separately. The one that we have over here has and there are several components that I want to point out. So I have a beaker on both sides of this thing. That beaker contains a solution. Notice that both of these are 1 molar solutions. Standard conditions indicate 1 molar solutions. We have something called an anode here. We have something called a salt bridge. We have something called a cathode here. And it says oxidation and reduction. Now remember, we talked about oxidation. So we lose electrons during oxidation. That happens on the left. So my oxidation by default should be on the left. Okay. The oxidation is where the anode occurs. So oxidation, anode, both vowels. So oxidation occurs at the anode. Reduction occurs at the cathode, red cat. That's how I remember that. And of course, our reduction is where those electrons are picked up so that we can turn this ion into a solid. So here we go from solid to ion. The other side we go from ion to solid. Now, when this process is happening, right, we're transferring electrons to make this happen, but then we're changing our charge balance. Okay, this is something we didn't talk about last time. In this beaker, we are now going to a situation where we have 2 plus and the electrons have left. So we end up with a bunch of 2 plus charges on this side. And over here, we had a bunch of 2 plus charges, which then react with the electrons and become neutral. So we now have one beaker that's positive and one that's negative. That doesn't physically happen. That never happens. And if it were to happen, they would go smashing into each other on the bench. The only way that this will actually work is if we make some connection between these 2 beakers. And that's done here through something called a salt bridge. That salt bridge allows different ions to travel through it. So you'll see that we get Cl minus coming from the salt bridge into the zinc side to balance the charge, and K plus coming from the salt bridge into this beaker so that we then have more positive charge to balance the electrons that have come over. Okay, so that's how our ions move. So on the oxidation side, we bring in an anion. On the reduction side, we bring in a cation. The electrons move from here over here. Okay, so from the negative anode to the positive cathode. All right. So Leo on the left, reduction on the right, oxidation on the left, reduction on the right, yada, 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 all of those wonderful things. And so we need to be familiar with this terminology for the anode and the cathode. And that goes with everything else that we talked about before, and that's why I'm trying to tie it all together. Now, this is a different one, and there's a reason that I showed this particular one. This has some cell potentials that are associated with it. We're going to talk about cell potentials next time, but I wanted to start introducing that idea here. Now, the problem that I have with this particular diagram is that my electrons are coming from the right and going to the left, which is not the way this should work. The reason that this is backwards is because this is actually from a physics source. So that's why they do things that way. But you'll see that everything is reversed from the way that we would talk about it. You'll notice that this particular reaction has this number with a voltage associated with it. So there's one for this half reaction, there's one for this half reaction, and then there's one for the overall reaction. Okay, that's something that we're going to be talking about next time, and that's going to help you determine which is going to be the anode, which is going to be the cathode, and what the overall cell is going to be able to produce. Why does that matter? Why is it important? Well, let's talk about this. You've probably had an experience with something like this in the past. You just didn't realize it. Ever driven a car, been in a car? They all have lead batteries. This is a battery. Okay, that's how it works. So we have a cell, one of those cells set up in it so that we can derive energy from it. So we set the way that this works. When it happens on its own, it gives off energy. And we can use that energy. We can harness it and use it. Okay. If you're using God, I'm losing my words. I'm getting old. I'm so sorry. Rechargeable battery, like on my phone. So lithium-ion battery. What happens is that reaction proceeds. It gives off energy, and then suddenly we have no more. And we plug it in, and we recharge the battery, which means that rather than going in the forward direction, so rather than going this way, it then goes this way. And we set it up to be able to perform that reaction again. So that's how that works. And there are a number of different things that use this. There are lithium-ion batteries. Those were very popular for a while. Now they explode all the time. We have nickel-cadmium batteries. We have lead storage batteries in our cars. Alkaline batteries that power all kinds of things. These are things that we deal with a lot. And the energy that they give up is small enough for us to be able to utilize and to be able to contain. It's not huge, but it's enough for us to work with. So that's how these are important to us. So it's important to start talking about what these things look like and how we can use them and understand them. Okay? So those are the things that we're going to talk about in terms of our voltaic cells. Now, one of the things that I said was that don't use these diagrams when you do the lab, because it's not set up this way. The way that the lab is done here at TTC, we don't use a salt bridge. We use something called a porous pot. And you'll need to look in the lab manual for a description of what a porous pot is and how it works comparative to a salt bridge. It performs the same function. It allows those counter ions to travel through it so that we have electric neutrality so we can do these reactions, but it is not a traditional salt bridge. So make sure when you turn that lab in, that's not what you're doing. Okay. Cell notation. So we have a cell. In this particular case, we're talking about this cell right here. So zinc going to zinc 2 plus 2 electrons, copper 2 plus 2 electrons going to copper. We had a 1 molar zinc sulfate. We have a 1 molar copper sulfate. And we talk about that in this way. Now, similar to what we did with non-ionic reactions, we're leaving out the stuff that we don't think is important. So it's here we're only putting what we care about. Now, you have the Zn solid, and then a single line that separates that from the Zn2 plus, which is listed as aqueous because that's in the aqueous phase, and its concentration of 1 molar. Okay, so that's one of those half reactions. And there's a single line here because there's a phase boundary. Solid is not liquid, solid is not aqueous, so there's a phase boundary between the two. That's what we mean. Notice we then have this double set of lines between this cell that was on the left and this cell that's on the right. Now, this is Cu2 plus aqueous, concentration for that, and a phase barrier to indicate the copper solid. Now, this should say solid. Let me back out for a second because I need to fix that before it kills me. And like I said, what you get uploaded will be fixed comparative to what you're looking at right now. So you will never see the typo on your slides. I have stopped posting the slides before I do the recording. So So there's that. So this directly represents the cell that we were looking at here. Now, one of the things that you can see here is that if it's not 1 molar solution, it will be indicated there. If it is a 1 molar solution, we can leave that off. It's implied if we don't include it. But I like to be thorough. I like to put everything in mind. So that's a total cell representation and a cell notation. Okay. Now, if a gas is involved, it's written as some electrode. In this case, we use platinum because it's an inert electrode. It doesn't actually involve itself in the reaction. There's an H2 gas in contact with H plus aqueous. And so because we require this electrode, the platinum electrode, it needs to be present. It needs phase boundary. There's a phase boundary between it and the H2 gas that's put in over it, and a phase boundary between that and the aqueous solution. The electrode, if it's an inert electrode that you're using, is always put on the outside of that. Now, platinum can be used in some of these cells, but it's often used as an inert electrode in gas situations. So oxidation is always on the left. Lose electrons oxidized, LEO on the left. Oxidation is the anode. Reduction is always on the right. Gain electrons reduced. Reduction on the right. Reduction is at the cathode. We get electrons coming from the plus charge since the current is defined as flowing in the opposite direction of the electrons. Okay. Standard conditions for the cells are 1 molar or 1 atmosphere if we're talking about gases. And then we want to talk about what is the balanced chemical equation for that process. Now, how do we get to a balanced chemical equation? Well, we know that in this particular cell, we're going from zinc solid to Zn2+. And in this side, we're going from Cu2+ to Cus. Okay, so when we talk about that, and I'm actually going to write this down here. Sorry, I didn't include this where I thought I should have. So we're going to have the Zns plus the Cu2+, because those are my two reactants, going to the Zn2+, plus the Cu solid. And the implication is that the electrons that have left the Zn have then traveled into the Cu2+ and given us those products. And I'll put that up for you. But okay. Let me torture myself a little. I'm not including the phases here because I can't write that much. Or at least I won't write that much. And it really doesn't matter how you write them in the equation. So when you're writing the balanced equation for this, it really doesn't matter how you write them. I tend to use the same conventions for this as I did before. So Zn plus Cu2+, because that's how it's written in my cell notation. And then going to Zn2+ plus Cu. So they stay paired. That's the way I do it. It doesn't really matter if that's how you do it. Anything is fine as long as it is the correct notation. Bear with me again just a second. I apologize. It's going to drive me crazy if I can fix it. Okay, never mind. Let's keep going. So what is our next? Oh, and let me do it. Okay. Sorry. Like, woman, can't you do this before you start talking? Yeah, you'd think so. Apparently, I haven't learned that yet. Okay, had to fix that. So what's the next thing we're going to talk about? Well, cell notation in cells. What is the purpose of the cell bridge? So we talked about this. We have electrons flowing one side to the other, but that means that we end up with a positive charge building on the side where the electrons left, and a negative or less positive on the part where the electrons are going. And so we have to move anions into the anode location and cations into the cathode location to keep that electrically neutral. That is something that is absolutely necessary. Okay. Questions, comments, problems? All right. Well, I have two examples that I'm going to set up here. So I want to talk about the cathode reaction, anode reaction, cathode reaction, the overall reaction for that, and the cell notation. Now I'm going to give you these. These are all shown right here. I'm going to talk about them in just a minute. And then I'm going to show you how these are drawn. So the pictures, the uploads that I have include the cell diagrams. You may be asked, and here's some of the things you might see. You might be asked to draw this. You might be asked to label all of these parts. You might be asked which direction do the electrons flow. What is the anode reaction? What is the cathode reaction? Which is the anode? Which is the cathode? Where does oxidation occur? Where does reduction occur? What's the oxidizing agent? What's the reducing agent? What's the overall cell potential? Which, again, we'll be talking about this next time, but that's something that can get asked. What could you potentially put in your salt bridge to make this work? And of course, the answer there is any salt. We tend to use the things that avoid precipitation. So things like sodium nitrate, which is always soluble, is always a good guess. KCl is a good guess because it's typically soluble. You know, things that aren't going to precipitate are things that we tend to prefer. So those are things that you could get asked. What is the cell notation for this particular cell? What does this single line represent? What does this double line represent? And all of those will have implications in the next class that we talk about as well. So that's part of the reason that those are things that we'll talk about those. As we talk about them, I hope to make sure to point out how they relate to what we've already done. Okay. So these are the two cells that we've got. We've got copper solid and copper, and silver solid. So I have copper solid and copper. All right. So copper solid goes to copper 2 plus and plus 2 electrons. That's why I lose electrons oxidize. And my cathode is 2 Ag plus, which is silver, plus 2 electrons going to 2 Ag. So since it said copper solid to copper, that's what I have here. Silver to silver solid, that means this ion to the solid, and that's why I have them in this order. Okay, that is again convention. Eventually we will talk about how you can determine which one should be the anode and which one is the cathode, but that's next time. I look at the overall reaction. So if I just add these two together, I get 2 Ag plus the Cu solid. It gives me 2 Ag solid plus Cu2 plus. The 2 electrons that were present, they disappear. Since this is my anode, this is the oxidation. If this is my cathode, this is my reduction. And the cell notation for this is Cu solid with a phase boundary, Cu2 plus, aqueous, and its concentration if I knew it. If I don't, I can leave that out. It's just a reminder. The double set of lines to indicate a new cell, Ag plus, aqueous, and the concentration, again, just a reminder, and the phase boundary to the Ag cell. Okay, so that's that particular setup there. And I'm not going to attempt to draw that cell here, which is why I'm uploading my notes for you. When we talk about magnesium solid going to magnesium and iron going to iron solid, again, same convention that I had last time until you can predict which direction it should go. That's how we're going to handle this. So my anode is magnesium solid going to magnesium 2 plus, just lose electrons oxidized. This is my oxidation at the anode. Here's my cathode, 2Fe3 plus going to Fe2 plus, gain electrons reduced. That happens at my cathode. So reduction at the cathode. Overall reaction, Mg solid plus 2Fe3 plus goes to Mg2 plus Fe2 plus. Notice one of the things that I've got to point out here is that we have no solid for, actually, Fixing things again, I know. So, sorry. We have no solid in this particular reaction. We're going from iron 3 plus to iron 2 plus. Both of those are aqueous components. So when we write our cell notation, similar to what we had for our gas, we have 2 Fe3 plus and then Fe2 plus over here and platinum. Thinking it's not helping. This has got to be 2 because that's a 1 electron process. Fixing again. And I'll tell you what I fixed and why I fixed it. And why it was bugging me. So I made some changes. So this used to say iron solid. There is no solid, so I had to take that out. We go from iron 3 to iron 2, which is shown here. We go from iron 3 to iron 2. That, because of the way it's balanced, since this is a 1 electron process and this is a 2 electron process, I need to have 2 irons and 2 Fe, 2 iron 3s and 2 iron 2s. When I write it in the cell notation, I have Fe3 plus and Fe2 plus, and again, there should be a concentration there. And then a phase boundary including the platinum. So the platinum is on the outside because it is used as an electrode in this system, but is not actually part of what we're looking at in terms of the electron process. So platinum is a platinum electrode used to transfer electrons. It's not part of the reaction. Only the iron cations are, but it's necessary to complete the cell. If you know the concentration, they must be put in this notation. If you don't, you can choose to omit them. I've left them in here as a reminder. Okay. So, as painful as that was to watch, that is what we have here, and those are the. So you'll get copies of the fixed slides, even though you saw the messed up ones in the lecture. You'll get copies of all of the drawings that I've done for this. Hopefully, that should be okay for you guys. I've talked a bit about having to write cell notations. Tell me what's the anode, what's the cathode, what's the overall reaction. Cell notation. Do I know what each of these boundaries mean? Do I know where to include concentrations if they're not 1 molar? How does that, eventually we'll talk about how does that affect things. Those are the kinds of things that you'll see. The practice on this particular set is not going to be particularly long because what's going to happen is after the next lecture, we'll do a lot of practice that includes all the stuff that we've already talked about, plus the stuff that we get in there. So this one is not going to be particularly long. This is just set up to be able to get us to the place where we're using all of that information. We have to have the information before we can use it. So here's where we're getting it. All right. So that is everything that I have was that little practice that we just did. And I will put up a practice thing to excuse me, specifically talk about these issues. And then, like I said, after the next one, we'll get into much more detail about what do we do with that, how is it useful, yada, yada, yada. So this will be a fairly short lecture and practice. Hopefully that will be okay with you guys. Like I said, I hope you guys are doing well, and I will talk to you again soon. Thanks, guys. Glad to talk to you.